So recording will be initiated momentarily. So let's see what happens. Everybody do your web assigns and just make sure you do the practices many times. And hopefully we're recording in a moment. There we go. And let's go to the PowerPoint again. Hearing. Hearing is not only perception of sound, but it's maintaining posture and balance, knowing the position of our head as we move it around, and also as we're moving to have perception of our movement so that we hopefully don't fall and break a bone or crack our skull. So let's look at the parts of the ear. So you should know about the external acoustic canal, the tympanic membrane, the auditory ossicles, which vibrate and cause the oval window to vibrate. These bones amplify the sound. That sound becomes waves within the cochlea, and we hear based upon the vibration along the nerves connected in the length of the cochlea. We have semicircular canals that we have the facial nerve coming in. We also have the vestibular cochlear nerve, the eighth cranial nerve, and that's getting information from the vestibule and so on, and the semicircular canals. And this is involved in dynamic and static equilibrium. The cochlear nerve takes messages from the cochlea, which looks like a snail. That's what cochlea is Latin for snail. I think something like that, or seashell. So we have this system takes care of hearing and balance. If you look closely at the auditory ossicles, we have the eardrum attached to the malleus, incus, and stapes. And the round window is there so that waves that are initiated in the fluid of the cochlea is able to be, the energy needs to be dissipated or dampened or reduced by vibrations of the round window. We can also look at the semicircular canals again, and the semicircular canals and the utricle and the saccule. Those are organs that stimulate and respond to movement, and by the movement of little rocks called ear stones, and I can't think what it's called. I'll get to that in a moment. So we'll have this fluid in the cross section through the semicircular canals, and the different density of the fluid in the cochlea and in the semicircular canals is related to the generation of position information and hearing information. So within the ear, we have these hair cells called stereocilia, and depending upon the direction of stimulation, we get inhibitory inhibition of the hair cell signal, and the direction stimulates the hair cells. So depending on the frequency and amplitude of sound waves and the bending of the stereocilia, we can hear, and that's another amazing transformation of information. So the semicircular connects, connected to the utricle. There's a gelatinous mass in there, and it's very has little stones in there, and the movement of those stones will cause information on the position of your head, both statically and dynamic movement. Okay, otoliths, that's it, otoliths. Ear stones. It's not how you get stoned, but it's how you hear. You get stoned by doing other things. I'm sure nobody knows anything about that. I won't comment on that because, well, I did try some drugs when I was younger. Not a lot, just a few. So we mentioned the vestibular nerve and the cochlear nerve. So the vestibular complex includes the semicircular canals and the saccule and the utricle and the vestibular region. And this cupola responds to the movement of the fluid around it, and that's going to indicate what direction your head is rotating. And so if we keep looking, we have these little stones called otoliths. And as we move our head, they move in particular directions. And these calcium carbonate otoliths will tell us the position of our head and also movement. Lithotripsy, if you know what lithotripsy is, that's when you use sound to break up stone. So litho means stone. That doesn't mean stoned. So the bending of these, the movement of these otoliths, and depending upon the direction of moving, the bending of the hair cells will either increase or reduce nerve activity, and that's how we figure out with our brain processing this information, we figure out the position of our head. So what about hearing? So sound waves vibrate the auditory ossicles and the bending of this basilar membrane. And we'll see that the hair cells are in the basilar membrane. And depending on the long position of this coiled snail, depending on the position and amplitude, we can distinguish between frequency and amplitude of sound. So depending on where the wave ends up causing bending of these nerve cells just above the basilar membrane, the bending of the nerve cells leads to the basilar membrane. And notice we have spiral ganglion, we have ganglion, which takes that information through the cochlear nerve to the auditory center. So if we look at the process of hearing, you start with sound waves bending the auditory ossicles. The vibration at the auditory window sends waves into the endolymph in the cochlear duct, the paralymph in the tympanic and the vestibular duct, and the movement of that fluid, depending upon its frequency and its amplitude, is going to cause vibration in varying parts of the cochlear canal, cochlear duct above the vestibular membrane, and below that is the hair cells in the basilar membrane, and that information is processed, and when it's processed, it's analyzed in the auditory cortex, and we're able to distinguish a lot of amplitude at different frequencies. Okay, so that's exciting, right? Did you hear that? Auditory pathways. Let's get, so the auditory pathways is going to be through the vestibular nerve and the cochlear nerve. And that goes through again the relay point of the thalamus, and then to the auditory cortex in the temporal lobe. Okay, that's it. So let's stop that. Let's go back here and stop recording. Stop recording.